I'm going to talk a little about your quiz here, see if we can help you out. I'm going to start on question 2. So this is about different types of acid-base theory. Here's the thing. Alphabetically, through these names, the concepts get more complex. So starting as simply as possible with Arrhenius, the Arrhenius theory is that an acid directly gives H plus to solution, or donates a proton, because H plus is a proton. And bases, since they have any basic solution will have a high hydroxide concentration. Arrhenius theory says that bases directly put hydroxide OH minus ions into solution. But Bronsted-Lowry, that's the next level up, going A to B. So the Bronsted-Lowry bases are defined as anything that accepts a proton or that bonds to an H plus. And in a kind of roundabout way, the H plus gets removed from the solution and OH minus gets added in the kind of roundabout way. So this Bronsted-Lowry is all about donating and accepting protons. So we're looking at the bottom one here. Now let's look at question 1 and think about question 1 in terms of Bronsted-Lowry acid-base theory. And we just have to ask ourselves, what is donating a proton? What is accepting a proton? It looks like the water donated an H plus, and the ammonia accepted it. And I'll let you guys figure out what that means in terms of which is an acid and which is a base. Okay, we got similar thing going on here. So back to the acid and base theory. Arrhenius is simple. Bronsted-Lowry gets a little more complex. And then Lewis acids and bases, that has to do with donating electron pairs or accepting electron pairs. Lewis acids accept an electron pair. Lewis bases donate an electron pair. And amines with nitrogen act as Lewis bases. They have nitrogens usually have an electron pair sticking out of them that gets donated somewhere. So let's see. What's probably going to happen is the electron pair on the nitrogen is going to grab an H plus off of water, and the water is going to be left as OH minus, and then you're going to get an extra hydrogen and an extra plus charge on your methylamine. You guys can handle this one. These all look strong, right? Metal hydroxides, generally strong bases, but we can recognize this as basically ammonia, which is a weak base. Let's see, the acid, acetic acid, is going to donate an H plus because that's what acids do. So the water is going to gain an H plus. So we're looking at A, D, or E. And then we have to think about what's going to be left of this acetic acid, and it's going to no longer have an H. And it's going to be, it's going to lose a positive charge too, so it's going to be negative like this, and it's not going to have the H anymore. So this, this looks like the right answer here. And it should be the conjugate base of acetic acid, and it does look like it is. Right, a solution is not neutral. Let me just point to this bottom one here. This should be a familiar equation from your acid-base flowchart. And this works for any concentration of hydronium or hydroxide. As one goes up, the other goes down. So this is true for acids, bases, and neutral solutions. Ooh, this one involves math. I'm going to let you guys do that. If you need to, refer to that acid-base flowchart with all your equations. Okay, so this might be a little tricky. When you're talking about the pH of salts, what we want to do is figure out the cation and the anion, ask ourselves about the conjugates of those. Okay, so I devised a plan to approach this. If it's going to form a basic solution, that means the anion is going to be basic. The cation is, not usually going to have basic properties. So we want an anion that has significant basic strength, which means its conjugate acid should be weak. Because remember, the weaker the conjugate acid, the stronger the conjugate base. This stuff, ClO4, its conjugate acid, HClO4, that's one of the strong acids that I forget sometimes. So this ClO4 would be a weak base. Let's see, Cl, its conjugate is HCl, the strong acid. So again, Cl is going to be a weak base. There's ClO4 again. That's its conjugate, the strong acid. Okay, what about this stuff? CH3COO, that looks like a carboxylate group, which is the conjugate of a carboxylic acid. Carboxylic acids are weak. So, this actually looks like acetate, the conjugate base of vinegar, conjugate base of acetic acid. So, since this is the conjugate base of a weak acid, it has significant basicity. Let's ask ourselves, is it canceled out by the acidity of the cation? No, because the conjugate of lithium would be lithium hydroxide, which is a strong base. So lithium itself would be a very, very weak acid. So here you have something with significant base strength and something without acid strength here. So this looks like our answer. And normal table salt, the conjugates are both strong, hydrochloric acid and sodium hydroxide. So if their conjugates are strong, they're both very weak in terms of their acidity and basicity. You guys can do this one. Check out the, if you need a hint, check out the Henderson-Hasselbalch equation. Which combination of solutions is the best choice for making a buffer solution? Well, we want about as much acid and base, so like maybe equal numbers of moles of acid and base. Here, the conjugate base, there's not a whole lot of it. So if we added acid, we'd use up all our base. It would react all the base real fast. Strong acids and bases aren't generally good for making buffer solutions. Here's a weak acid, weak base pair. acid and its conjugate, so that's good. Generally, buffers are an acid and its conjugate base. So this works pretty well. Here's another one where you hardly have any base, and this is a strong acid, so it's not likely that you're going to use a strong acid in a buffer solution. Hold on, let me read this. Oh, okay, never mind. You guys can do this one. Okay, so if there's more acid than conjugate base in your buffer, it just this is pretty intuitive. The buffer solution is going to be a little more acidic than if there was equal amounts of conjugate base and conjugate acid. So yeah, and again, more acidity means a lower pH. And remember, a buffer solution doesn't necessarily buffer exactly at 7. It could buffer, anywhere over the pH scale. Okay, so this is a weak acid and its conjugate base. Okay, so this one's a little tricky. Maybe think Henderson-Hasselbalch equation. The pH is the pKa plus log of conjugate base over conjugate acid. Now, if we dilute the whole solution, we're changing the concentration both of the conjugate base and the conjugate acid. So that ratio of conjugate base over acid is going to stay the same. So just looking at the Henderson-Hasselbalch equation, our pH shouldn't really change much when we just dilute. Okay, so there's a little more conjugate acid than conjugate base, so it's going to be a little more acidic than its pKa value. Hold on, let me read this one. Okay, here's the deal with this one. You're basically going exactly to the equivalence point. And I'm not going to tell you the answer for this because this is exactly what you guys did in a lab. So you guys saw this happen. It's a titration of a weak acid with a strong base. And there's also graphs of this in your book that are really, there's some good graphs in your book of different titrations, including weak acid, strong base. This is just kind of fact question. Oh, and that brings us to the end. Okay. Well, yeah. Good luck on your quiz. Let me know if you have any further questions. And take care. I'll see you guys next week with another quiz.